Testing. 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 Alright, I think this is working. Alright, how's it going, Deadly Data? And welcome to another Hoopo stream. Today we're going to be reading a DeepMind paper. So closing off the week with a absolute monster of a paper. This paper is very long. It's 32 pages long. So we'll see if we can actually get through the whole thing. We might have to skim through some parts. But August 7th, 2023, so just a handful of days old. We got all kinds of people on this paper. And it's called AlphaStar Unplugged, Large-Scale Offline Reinforcement Learning. So obviously reinforcement learning is a type of learning where you're using reinforcement, generally from an environment in the form of a reward function. The offline here refers to the fact that the interaction isn't happening kind of in real time. A lot of times reinforcement learning systems, they store experience or their interactions with the environment in what's called a replay buffer, which is basically, you could think of it like a recording of every single game of Go that was played, and then you can train or learn from that offline experience. So large-scale offline reinforcement learning is a reinforcement learning where you're learning from these large databases of previously collected experience. So you're not interacting with the world and it's reacting back immediately, which is a different kind of, leads to different kinds of algorithms and such. Okay, so let's look at this abstract. StarCraft 2 is a real-time strategy game. It's a video game where you basically control these little units and you make a little base and then you build buildings and then the buildings have different units and then eventually the whole point of the game is to basically destroy all the enemy pieces. So it's kind of like chess, but way more complicated. How's it going, Ite? One of the most challenging simulated reinforcement learning environments. So simulated because it's a video game, so you can simulate it perfectly. You can recreate situations perfectly, and so on. So unlike the real world, it is partially observable. Partially observable means you cannot know the full state. So a game like chess is fully observable. You know where all your pieces are, and you know where all your enemies' pieces are, and you know every single piece on the board. You have full observability of the board. But StarCraft is not like that. StarCraft is partially observable. You can only see your pieces, and then maybe you can see some of the enemy pieces, but you certainly can't see the whole map, and you certainly can't see all the pieces that the opponent has. Stochastic just means random. Multi-agent just means more than 2-player, 3-player, 4-player. You can even have 8-player games, I'm pretty sure. Mastering StarCraft 2 requires strategic planning over long time horizons. So you need to have a long strategy about what you're going to do this game, and then also that's called macro sometimes in the RTS community, and then you have kind of real-time low-level execution, which is called micro, which is your ability to move a unit just a little bit to the left here so it can maybe get one more arrow off or something like that. So basically you need to have this combination of kind of a longer-term planning and then a low-level planning or fast control loop planning. Okay, it has an active professional competitive scene. StarCraft 2 is uniquely suited for advancing offline RL algorithms, both because of its challenging nature and because Blizzard has released a massive dataset of millions of StarCraft 2 games played by human players. Okay, so this massive dataset of millions of StarCraft 2 games played by human players, that's the exact type of dataset in which you could use large-scale offline reinforcement learning. So they're kind of setting up some of the reasoning why they decided to use offline reinforcement learning here. This paper leverages and establishes a benchmark, AlphaStar Unplugged, introducing unprecedented challenges for offline reinforcement learning. We define a dataset, a subset of Blizzard's release, tools standardizing an API for machine learning method. So some tools, some APIs. So they're basically going to release this entire data set along with all the ways to interact with it as a benchmark, which I think is very useful. And part of that is that there's still a lot of people in the reinforcement learning community that are doing things on these like Atari video games. Atari Sweet RL. Something like this. But basically, there's a bunch of Atari video games that are available in much the same way with tools and an API and so on, so you can interact with them. And a lot of research is being done on these type of games. But it's starting to get to the point where the research, I think, is overfitting to these types of games, where they're finding what they think are tricks that are applicable to all of reinforcement learning, but in reality, those aren't applicable to all of reinforcement learning. Those tricks only work because of the limited kind of properties and distribution that is represented by these Atari suites. And you could think of chess and Go as also kind of limited in the same way, where they're kind of these fully observable 2D games where somebody has to win and there's a limited kind of time period of the game and so on. And I feel like for reinforcement learning to advance to the next level, we need to make these environments much more complicated, much more rich, and much more nuanced. And I think StarCraft could be that game. So having a set of tools and open sourcing, I don't know if they're open sourcing it, but at least making it available as a benchmark, I think is a big step for reinforcement learning research. Evaluation protocol is a way to evaluate, which is obviously crucial if you're going to be releasing a benchmark. So if the tricks might not be universally applicable, people say that the algorithm you can get from games can be used in other fields heavily. Is that correct? Kinda, but like a lot of times when you see in a reinforcement learning paper, they say, oh, okay, well, we found this trick and it works for this, and it transfers, right? But like what they refer to when they say it transfers, they said they tried it in this game and it also works in this game, right? But there's kind of like a myopicness to that statement, where in reality, any game in this Atari suite is basically the same fucking game, right? And even anything in this Atari suite compared to chess, like it's still the same constrained 2D perfectly simulatable world, right? So I think that your statement deadly data depends on your definition of universally applicable. Like if I can take a Aura algorithm that works or a trick that works in these games and apply it on a robot in the real world, now you're talking. Now we're okay, well, what did you do? How did it help? But a lot of times when people talk about like multitask reinforcement learning or reinforcement learning agents that are general enough and can transfer to new tasks, they're still within this within this very constrained sphere of tasks that they think are broad, but they're really very narrow. Yeah, it'll never be a thing where, for example, something discovered in a game and then applied on a project like AlphaFold. Yeah, I think that AlphaFold and Gemini, which is reinforcement learning on top of language models, which is, we don't know many details about it, but we know that DeepMind is working on that. And that's one of the reasons why I keep reading these DeepMind papers, is because I think there is something to reinforcement learning. Like you can't beat the master Go person with nothing, right? So there is some truth to this. There is some universal applicability of reinforcement learning to any kind of game, whether it's protein folding or robotics or anything. So there is something there. I'm just more skeptical towards individual little tricks and individual little intuitions that people build, that I think a lot of those might be constrained, but the overall category as a whole of reinforcement learning is definitely works, in the sense that we have some pretty impressive demos and real world examples of it working. But yeah, the combination of reinforcement learning on top of something like a GPT-5 that is currently being worked on in DeepMind under the name Gemini, like that's that to me is not just AGI, because I'm a believer that GPT-4 is API, GPT-3 was AGI to some extent, but I feel like what they're working on there, that's actual super intelligence. So we might be years away from an artificial super intelligence. Okay, we present baseline agents, including behavior cloning. These are other types of reinforcement learning. Behavior cloning is whenever you try to clone a behavior, aka mimicking a behavior. Usually the behavior is a human playing the game. Offline variants of actor-critic. So actor-critic is another type of reinforcement learning algorithm where you basically have one network, one neural net that's the actor, another neural net that's the critic. Offline variant would be a variant of actor-critic that works with offline data. Mu0, another reinforcement learning algorithm that was pioneered by DeepMind. We improve the state-of-the-art agents using only offline data, and we achieve 90% win rate against previously unpublished AlphaStar behavior cloning agent. Yeah, and the impressive thing here is that's only offline data. So obviously the successes that you guys might be aware of, such as the chess or the Go, those are online, right? They play against themselves, so they can take novel actions and then see what happens when they take that novel action. But when you're doing offline reinforcement learning, you don't have that ability, right? You only have historical games, so it's a completely different thing, right? They could not have trained a master Go agent that basically only had access to a bunch of historical Go games, because at that point it would basically just only be as good as the people that were playing in those historical games. I don't know. Okay. Let's go into this introduction here. And these might actually be the sections that are worth skipping because these generally tend to be just a little bit verbose. Dominated by online reinforcement learning. Must interact with the environment to learn. So that's online reinforcement learning. Our online RL paradigm achieved Atari, Dota 2, robotics. Exploration makes these algorithms unsuitable and unsafe for many real-world applications. I don't know about unsafe. I would say that it's probably still fine. In the offline setting, agents learn from a fixed data set previously logged by humans. So this is a good definition of offline. While the offline setting would enable RL in real-world applications, most offline RL benchmarks have mostly focused on simple environments and data produced by RL agents. So more challenging benchmarks are needed. So they share the same kind of idea that I was talking about, where we kind of need better benchmarks. I think Atari has been beat to death, and even chess and Go are kind of beat to death. We need like something much more rich, and I think StarCraft and video games are the perfect, or at least much more complicated video games are the perfect suitor for that. We introduce offline RL benchmark, which uses dataset derived from replays of millions of humans playing the multiplayer competitive game of StarCraft. StarCraft continues to be one of the most complex simulated environments. Maybe. I think there's more complicated games than that. I would love to see the Total War series is like also kind of a real-time strategy game, but it has like this very complicated like campaign thing where you're like making alliances and like sending stuff and trading, and I'd love to see RL in those kind of environments as well. Mastering the game requires strategic planning and real-time low-level execution. And this is kind of maybe another point. I realize this is a 32-page paper and it's already taking me 20 minutes to get through this first page, but in some of these earlier works, like the Dota 2 paper here, or the Dota 2 RL algorithm, there was basically, I think, a cheese strategy based on real-time low-level execution, where basically these RL agents just learned how to be very, very good at hitting specific skill shots and basically doing these very fine kind of motor movements. You can think of it that way, how like some people, when they play video games, they're really good at just like the aiming and the clicking and the hitting the right button at the right time, versus other people are more thinking these long-term strategies. And I think for some of these earlier RL video game attempts, such as Dota 2, the success and kind of the superhuman performance was more at the level of just clicking the right buttons at the right time and being able to hit things that for a human would be very, very difficult to hit. And that's just because the RL agents kind of is able to act at a faster control loop than a human would. But I really haven't seen kind of like superhuman performance in video games such as Dota 2 and StarCraft in terms of the kind of high-level strategic planning. So that would be kind of cool if it comes up with like weird, interesting, novel strategies that humans haven't come up with. StarCraft 2 independent leaderboard constitutes a rich and abundant source of data. It's the beginning of any learning project is you got a good data set. League of Legends or Dota is a good too, yeah. Focusing on mechanics first and then the strategy. I think it's easier to win by getting really good at the mechanics if you're a reinforcement learning algorithm. The strategy is a much harder path to getting good reward. We released the most challenging large-scale offline RL benchmark. Canonical agents notes that removing the environment interactions from the training loop significantly lowers the compute demands of StarCraft 2. So here they're saying that if you have a bunch of offline data, it's a lot easier to feed that through a neural net in the form of batches rather than having to actually run a StarCraft 2 game and then take an action, get the screen, save the screen, put that into a batch of data and send it. So like offline reinforcement learning is just inherently going to be way faster in terms of the training loop and the ability to kind of feed data rather than having to do it online where you're having to wait to actually simulate the game. StarCraft 2 would also make sense if the RL masters the micro. Yeah, and that's I think I'm not like familiar with how the AI is implemented in these games, like the actual AI that you run. It's like heuristic based, right? Some human just programmed it, but I think that they do that as well, right? So like in the AI that comes with these games, it's like the way that the AI is good is that it's just really good at micro. It just basically individually controls every single unit. Familiarities of state-of-the-art do not perform well. Q function, some older approaches here all fail to outperform. However, is all provided to design successful agents. All of our successful approaches are so-called one-step offline approaches. Okay, I don't know what the one-step refers to there. Our best performant agents follow a two-step recipe. Okay, so maybe it's like how pre-training fine-tuning would be two-step, and then one-step would just be kind of like a zero shot where you just pre-train and then see how good it works without any additional fine-tuning. First, train a model to estimate the behavior policy and behavior value. So the behavior policy, sometimes also called the actor, and then the behavior value, sometimes also called the critic. Then use the behavior value function to improve the policy either while training or during inference. We believe sharing these insights will be valuable. Okay. StarCraft 2 for offline reinforcement learning. Real-time strategy game in which players compete to control a shared map. Several modes such as team games and blah, blah, blah. Consider StarCraft as a two-player game. Well, that's fucking lame. They literally set it up here, multi-agent. Yeah, here, multi-agent. You're telling me that multi-agent is just two? Like, damn, I thought this was going to be more. I thought they were going to have more players than that. High-level reasoning, numerous strategies. Start the game by selecting one of the races, blah, blah, blah. Each game is played on several maps, have different terrain. Been played online. Millions of games, including professional players. I think the professional players is an important part, right? I think that having a benchmark where the human level of performance, you have a very wide variance, right? It's like for StarCraft, there's lots of humans who are mediocre at StarCraft, lots of humans who are okay at StarCraft, and lots of humans who are pretty good at StarCraft, and lots of humans who are even pro at StarCraft, right? And they've literally spent like a huge chunk of their lives just getting very, very good at this game. So we have a very good idea of like the minimum and maximum level that a human can get to in this game versus other Atari games like this, right? Like, do we really know what the maximum human performance is for one of these Atari games? I don't think anybody spent the amount of hours that someone spent playing StarCraft playing one of these Atari games. So these games like Go and chess and StarCraft are interesting in that way, where there are cohorts of humans that have basically dedicated their lives to getting as good as possible to these games. So if you can show that you're better than these humans that have spent decades playing these games, then there's probably something there, right? And we've probably achieved superhuman performance. Action space. So this is the space of all possible actions that you can take in an environment. So learning the performance depends greatly on the availability of different state action pairs in the data. So state action pairs is basically a fancy way of saying, here's the current state of the game, and here's the action that I took, and then here's the state of the game afterwards, right? So if I have a one unit here, and I click over here, and then the unit moves, and that's basically a state action pair. We call this coverage. The more state action pairs that are absent, the lower the coverage, the more challenging the problem is. StarCraft 2 has a highly structured action space, must select an action type, select a subset of its units, and then select a target for the action, and decide when to observe and act next. There are approximately 10 to the 26 possible actions per game step, which is fucking huge. And I think another kind of way that these RL algorithms cheat here is that their action space is different than your action space. So you as a human, your action space is the number of keys on your keyboard and then the XY position of your mouse, right? So whenever you're microing something in StarCraft, you're literally clicking on a unit and then clicking on somewhere in the ground, right? Like you're moving your mouse cursor in an XY position. These reinforcement learning algorithms they're not moving a mouse around. If they tried to move a mouse around and click on things, it would be so much harder that nobody would be able to solve them. So part of the reason that they work is because they can instantly tell this unit over here, move over here, and then the game just does it for them. So that's another important thing to realize, is that the humans are doing this in a different action space because they're doing it with a mouse XY position and then the keys on their keyboard, versus the RL agent basically can go perfectly down to the actual game code level and like say, this thing move here, this thing move here, this building do this building do that, and it can do it all at the same time, which is part of the reason that it's so good at micro. Okay, stochastic environments may need many more trajectories to obtain high state action coverage. So if you have a game that has a bunch of randomness in it, then you're probably going to need a lot of games in order to, or a lot more coverage over all possible states of that game, all possible state action pairs in that game. StarCraft 2 is imperfect information game. Players only have information about opponent units, so this is the partially observable nature. StarCraft 2, access to millions of human replays. So there you go. So partial observability, data, and the stochasticity of the environment are the three reasons why they pick StarCraft. I always wondered whether Blizzard pays DeepMind money to do research on StarCraft, or whether DeepMind pays Blizzard money to use StarCraft. I'm not exactly sure who would be paying who, or whether they even like talk to each other. That'd be kind of interesting to see what the relationship between those two institutions looks like. Training setup. We fix a data set and set of rules in order to have a fair comparison. Propose a set of metrics. Provide a set or a number of well-tuned baseline agents. So baselines are basically when you have a benchmark, right, you're going to be comparing your performance on the benchmark to the performance of other things on the benchmark. So if you release a benchmark and you have nothing to compare against, it's not a very useful benchmark. So when you release a benchmark, generally you include certain baselines, and those baselines are basically examples of, here's what this agent performs on this, here's what this agent performs on this, here's what this agent performs on that, right? So as part of releasing this benchmark, they're releasing some baselines to give you an idea of where your performance is when you try to solve something on that benchmark. Open source code. Massive engineering performs. We provide a well-tuned behavior cloning agent, which forms the backbone for all agents presented in this paper. Somehow, I doubt that they're open sourcing all the code. DeepMind is one of the most secretive and kind of like cagey AI organizations in the world. They're a little bit over intense. They kind of have that vibe that they feel like they shouldn't share what they work on, so they feel justified in the fact that they never release any code. So it's a little bit unusual for them to release code like that, so we'll see what they actually release. My intuition is that it's probably not much at all. 20 million StarCraft games, so this specific version of StarCraft 4.8.2 come from the StarCraft 2 ladder, which is the official. Each player is rated by an MMR, so matchmaking rating, and here is the number of episodes, which are basically, I guess, games, and at roughly what MMR. So I don't really know what an MMR of 5500 is in StarCraft, but kind of it would make sense that you have a lot more examples of mediocre games and then just a handful of examples of very high-level games. Okay. Consider two-player games. Represents a total of more than 30 years of game played. Blah, blah, blah. Older, more recent. Map pool changes. Average two-player is about 11 minutes long. So that's your average game there. Corresponds to approximately 15,000 internal game steps. So 15,000 steps is the length of one episode. Deadly data. I would imagine Blizzard wouldn't let them release the code since it might give them the opportunity for people to run those in real games, or are the power requirements too high to run for a regular person? I think we're still, the inference would be hard to do. You could probably figure out a way of doing it, but at that point, like, you're just paying for like a server rack to win StarCraft games for you. I don't know. I'd be curious to know how much people bought in StarCraft. They probably use bots for kind of automating other tasks, so like bots that automatically tell them things. I know that bots and AI are actually a huge problem in poker. So I've heard that in a lot of online poker, it's basically you're rarely playing against humans. Even the people who are sitting there and pretending to be humans, they're just like, they have on a second screen, they have like an actual poker bot that's telling them what move to play. So yeah, maybe video games just kind of lose their allure once we have AIs that you can run on your computer that just play it at a superhuman level. I tend to play RuneScape and WoW. You see them a lot. Yeah, I've played those games as well, but you don't really see them in like competitive play. I feel like the bots are more to automate like low-level tasks like fishing. We shorten the trajectories, adding a delay. Discuss the effective length of the episode by 12 times. Okay, so there's already some fuckery happening here where they're shortening trajectories by discarding internal steps. And then that allows them to reduce the length of the episode by 12. So basically they're going from 15,000 game steps per episode to something more like 5,000 game steps per episode, right? So like an order of 10. Also contains metadata, which can be 1 for a victory, 0 for a draw, -1 for a defeat, as well as the MMR of each player. Based online, blah, blah, blah. Okay. The data is anonymized and does not contain personal information. During the training, we do... Okay, so this is training restrictions. Here you have the training procedure. You have the data set, which is replaying. These are kind of reinforcement learning terminology here. Replay, trajectory, batch trajectories, but they have an analogous terminology that you guys are probably more familiar with, right? So your data loader is just the same type of data loader that you would use in training a neural net, right? It basically just takes your data set and puts it into, picks specific ones, either randomly or with some specific sampling strategy. Those are called trajectories, so specific games, right? So one game is going to be one trajectory, and then you put those on a queue, and then you're going to batch them, put them in a batch so that you can feed that entire batch into a GPU, which is containing a neural net, which is the policy or the learner, and then the learner is going to basically say, okay, well, this state, I would take this action, and then what reward would I get from that, right? What value would I get from that? So this is the value loss, the policy loss, and then eventually you use that to push gradients into the neural net. That's your policy, and the neural net, that's your value. There's two neural nets here, one for the policy, one for the value function, and then you update the network weights. And then once you have your updated network weights, then you can go ahead and use those to play StarCraft, and that's what you're doing here with the evaluator. You're using your agent, which is your policy, to take actions in the environment. The environment tells you how it changes according to that action, and that's it. That's the basic training and evaluation procedure. Agents are trained to play all three races. Okay, so there's different races you can play in StarCraft, and they have different strategies, different units. So previously, I guess they were constrained. Tried to make use of the same number of training inputs whenever possible, on the order of Kmax equals 10 to the 10th observation in total. Final performance eventually saturates is a meaningful comparison metric, assuming each method is given enough compute budget. Numerous metrics can be used to evaluate the agents. It's easiest to compute to simply look at the value of the loss function. So the loss function... Numerous metrics. Okay, never mind. This is not what I thought I was going to talk about here. I found that the terminology in RL keeps changing between papers, which is confusing as fuck. Yes, agreed. I think there's kind of an unfortunate reality that a lot of reinforcement learning, it has kind of all the bad parts about academic bureaucracy, where basically you have this accumulation of terminology and citations and who came up with what idea, and like you end up having a world where a lot of the brain power and memory of people is basically storing all these like unnecessary terminology, and just makes everything more confusing for no reason. So I don't know. I think that's just the result of reinforcement learning being an academic thing, but I feel like it's going to get simplified, and we'll stop calling things policies and actor critics and trajectories, and we don't need to have that terminology anymore. Perhaps the most informative and most difficult to compute would evaluate the agent against a wide panel of human players. So this would be kind of the best possible way to evaluate one of these agents. We evaluate our agents by playing repeated games against a fixed selection of 7 opponents. Okay, so they basically play the AIs that come built into the game. We evaluate the agents against a very hard bot, since it's significantly less expensive. To tune hyperparameters and discard non-promising experiments. That's a little sketch. So basically, they're tuning their hyperparameters based on the performance of the AI agent against the very hard bot. Combine these win rates into 2 aggregated metrics. Robustness is computed as 1 minus the minimum win rate. Okay, so here are the 6 reference agents. So they're baselines, which can be used as both baselines. Underlying system dynamics can be described by a Markov decision process. So it wouldn't be a reinforcement learning paper if you didn't have a Markov decision process paragraph. And here we go. So this is the basic MDP paragraph. Look how condensed they've gotten it at this point. It's basically just one. So an MDP, you have your state. Here you go, finite set of states and actions. A transition distribution. So some distribution that tells you, given a certain state and action, how do you get to the next state? And you call that the state transition distribution. For all state, action, and then next state pairs, so S, A, and then S, a reward function, R, which maps from states to reward. And this is where you have to basically have a human to design this reward function, and an initial state distribution, I. In the offline setting, the agent does not interact with the MDP, but learns only from a dataset D containing episodes made of sequences of states and actions. So you have episodes, which are sequences of state-action pairs. We denote S in the sequence of all states and length of S as its length. A policy is a probability distribution over actions given a state. So again, kind of like needless formalism here. The policy is going to be the actual neural net that takes the actions. It's going to be the actual agent. A dataset D is assumed to have been generated by following an unknown behavior policy mu. So this is the human unknown behavior policy mu, such that the action at time t is coming from this mu, which is conditioned on S of t. But even this here is actually technically wrong, because the human is not just conditioned on S of t. The human is using all this other prior knowledge to make that decision. So there's a lot more conditioning going on there. Observed states are a subset of internal game steps. We call delay the number of internal game steps between two observed internal game steps, which corresponds to the amount of real-time elapsed between two observations. So this is the trick that they were saying up here, where they're basically shortening the games, right? We discard internal steps in between interesting things. So I think that's what they're going to call the delay here. The environment must be provided with a number of internal steps to skip until the next observation. Therefore, the delay must be part of the action. Okay, so the agent can basically choose to delay if there's nothing happening. Given a policy and a state, we define the expected discounted return. So this is just a fancy way of saying how much reward are we going to get at this current state, taking that action, right? So obviously you have some reward function, which is the human telling you this is good, this is bad. Winning the game is good, losing the game is bad. And then discounted return refers to the fact that the reward at some point in the future is going to be discounted. So it's not as good to get a reward later than it is to get a reward now. And the expected is just because it's the expected value of that. As the expected sum of the discounted rewards if we follow the policy from that state. The discount between two steps is based on the delay between the steps. In the case of StarCraft 2, the reward is the win-loss signal. So it can only be non-zero on the last step of the episode. Yeah, and that's kind of what makes... This is called sparse rewards, where the reward signal is very sparse. Basically, it's just a bunch of zeros all the way until the very end, where you get a 1 for winning and a 0 for losing. Sorry about that. So it's usually very hard to do reinforcement learning without a dense, rich reward signal. Okay, so here we have basically this paragraph here, but written in math. We have the discounted rewards. The expected discounted return is the expected value, this fancy E, of the discount factor. This is that gamma here, which is to the DTS power, because let's say your discount factor is 0.9, then 0.9 would be the reward for the next step. The reward for two steps would be 0.9 times 0.9, then 0.9 times 0.9 times 0.9. So you can see how as you basically multiply that 0.9 times itself more and more times, it starts becoming a smaller and smaller number, which means that the reward here, R of S, gets smaller and smaller and smaller as it goes further and further away from you in time. So that's how the discount factor changes the reward. But yeah, it's the expected value of this. And here we have all the little caveats. So the state at time k plus 1 is coming from your environment, which is basically giving you that state conditioned on SKAK, the action at time k, the state at time k. The action at time k is coming from your policy pi, which is conditioned on the state at time k. And all k is greater than or equal to t, for all k greater than or equal to t. And what else? We got DTS equals length of S minus 1 over k times dA of k. So I think this is the fact that you're skipping, is basically what this is. Remaining number of internal game steps until the end of the episode. Okay. RS is the reward. Let me at least highlight these, and then DS is the remaining number of internal game steps. The goal of offline RL is to find a policy pi which maximizes that. During the training, we refer to the policy as the train to estimate pi star as the target policy. Okay, so the target policy is the policy that is trained, and then you're going to have the unknown behavior policy is the human, because the human has some policy that we don't know, and we're basically trying to approximate that. We use v mu and v pi to denote the value functions for the behavior and the target policies, mu and pi, which are trained to estimate v mu and v pi. So these value functions here, v mu and v pi, these are also usually neural nets. Back in the day in reinforcement learning, these were actually tables. So there was actually like an explicit table of like, here is the reward for every single state and action pair. But now you're using a neural net, which is a neural net that is basically trying to estimate this value here, right? So you have one neural net, which is the policy, and the policy is saying, okay, I'm in this state, and I don't know what action to take. And eventually the policy says, okay, I don't know what action to take, but I'm going to take this action. What the value function says, okay, you're in this state. Here's what I think the reward is going to be if you ran this out to if you played for the rest of this game. This state is in this action gives you this reward. This state and this action gives you this reward. This state and this action gives you this reward. So it's an estimate of the value of that position, and I think that concept exists in games like chess and like that too, right? Like humans are using kind of like a value function where a person can kind of look at a board. A really good chess player can look at a board game or a board of chess, and they can look at that and they can say the expected reward of white is way better than the expected reward of black, right? There's like some notion of like this is a good place to be in for this person and a bad place to be in for that person. So that's what these value functions are trying to estimate. They're trying to kind of estimate this idea of like what is the expected discounted return, which is basically what is the value of this current state and place that I'm at in this game. All right, so now that I've confused the shit out of you guys by further mashing together a bunch of terminology, train the agent on rollouts, sequences of k consecutive time steps assembled into a mini batch of m independent rollouts. So rollouts are episodes. All of our experiments are based on the same agent architecture, improved version of the model. How is the neural network trained? I can understand the table, but in a game as SC2, can they even calculate the expected return? You can, yeah, because you have the entire game. So once you have the entire game, then you say, okay, well, at the very last step that I took, the reward is 1, which means that if my discount factor is 0.999, then the step that led to that step has a return of 0.999, and the step that led to that step has a return of 0.998, right? So if you're in a different place and then you suddenly come up into a state that at some point led to winning the game. So the reason it's not just all zeros is because at the very end you have 1 for winning and 0 for losing. So all the games that are winning, basically from that very last step, it just propagates all the way down into all of the state action tuples of that game where you won, and there's a small value that's saying, okay, this action in this state ultimately led to a win. So there must be something about this action in this state that is good. And on the other side, if you start from if you go to the very end and the game was a loss, and then you kind of let that trickle all the way down, what the value function is trying to learn is that, okay, this action in this state eventually led to a loss, so something is bad about this action in this state. So the return, all of it is coming from the win-loss signal, which is the 1 and the 0 at the very end. Hope that answered your question, Ite. All of our experiments are based on the same agent architecture. The full architecture is summarized on Figure 3. Can we get to it? This is Figure 4. Okay, so we skipped it. Figure 3. Here we go, Figure 3. Illustration of the architecture that we use for our reference agents, which are the baseline agents. Different types of data are denoted by different types of arrows. Vectors, units, or feature planes. Okay, so vectors are these filled in arrows. Units are the arrows with kind of like a lines, and then feature planes are these empty arrows. It's a very confusing terminology there. So blue is a trainable module, aka a neural net. Red is the output. I guess this is modality. So here we have vectors. Everything under here, I guess, is vectors. Everything here is units, and then here is feature planes. And then fixed operation is an op. So here we have just merging. So concatenation, scatter. And then the blue is the actual inputs. Okay. So what do we have as inputs to this system? We have vector inputs, previous vector arguments. Okay, so that is probably the output from a previous step or something. That's what I'm guessing here. One of these outputs is probably the value function. Unit inputs, previous unit arguments. So this is the information about the units, I guess. And then feature plane inputs. What the fuck is the feature plane? Did they describe that? Okay, actually, let's read this, and then, because I think they describe what these are. A list of features for each unit present and feature planes. Okay, so you have the height map, a topography of the map. You have the visibility map, area within the vision. You have creep, the area of the map covered by the Zerg creep. This is specific to StarCraft. Player relative. For each pixel, if a unit is present on this pixel, this indicates. So it's basically they're turning what is a visual game, StarCraft, into basically these feature maps with the resolution of 128 by 128. So they're extracting all this information from the game using hard-coded rules, such as all of these, right? What is pathable areas of the map, which can be used by ground units. So that information is explicitly stored in the form of a feature map, which is pixels of 128 by 128. So the actual reinforcement learning agent is not looking at what you're looking at. As a human, you're looking at all of this information rendered in the form of like an environment that looks realistic. But the reinforcement learning agent doesn't see that. It's not seeing the screen. What it's seeing is basically these 128 by 128 little like kind of thumbnail pictures of all these different things here in the map. Same thing with the units. It's not actually seeing the units in the way that you're seeing the units. What it sees is a bunch of vector of size 43 containing all the information that would be available. So it literally has omniscient vision. It sees everything instantaneously, versus you as a human, you're looking at one part of the screen, and if you wanted to look at something else on the screen, you have to move your eyes to look at that part of the screen, right? So it's a little bit cheating in that sense, where it kind of has omniscient vision of everything. It's getting everything in the screen, every possible, down to like the resolution possible, right? 512 possible things. Last known state of opponents' buildings, location of opponents' units, amount of minerals currently owned, amount of whatever Vespine gas currently owned, food use, food cap, larva count, army count, idle worker count, away race, previous details. So it's like all this information is just perfectly fed into it in the form of little vectors and these feature maps. Okay, let's go back. So that's what a feature map is, or the feature planes and the vectors and the units. So these are the inputs that are coming in. The current vector inputs and the previous vector inputs from the previous time step. The current unit inputs and the previous unit inputs from the last time step. And then the feature plane inputs, which is basically the map. So all of those are going fed into here, into these encoders. These encoders are specific to the input modality. So that's one thing to note. There's a different encoder for each modality of input here. Some of these encoders are being fed into this transformer here. Some of these are being fed into a multi-layered perceptron here. You see how what's coming out of this transformer is also being given here. So you see how the feature plane inputs are going through this encoder. They're merged with the unit inputs, fed into a ResNet, and then that's fed along, that's embedded, but then fed along with the transformer unit inputs into here in MLP. So there's a lot of complicated wiring here, but largely, basically, everything is getting fed everything. So this little MLP here, this optional memory, MLP, this stuff here has access to basically all of the game state, encoded and embedded. Here you have kind of a recurrent-like looking thing. Maybe not recurrent. This is just function, delay, queued, repeat. What does that mean? Delay and queued make me think there's some kind of weird recurrence going on here where this module waits and then sends again. I'm not exactly sure. Unit tags, target unit tags, pointer net, convnet. This is a very confusing flow. Oh, these are the outputs, or maybe unit tag world. Where is the actual output? Outputs is red. Logits, 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 logits. So logit means when you have a classification model, the last layer represents probabilities, but before you can think of them as probabilities between 0 and 1, which is done by putting them through a softmax, they're kind of just numbers, and those numbers are called logits, right? So in this case, you're choosing over a set of possible actions. So the neural net is, in a sense, classifying, given these sets of inputs, which of my actions should I take, right? It's kind of like a classification problem, which is, it always boils down to that, right? So maybe the raw logits of like, what action should I take given all this crap that I just fed in, that's what's going into, I guess this is the outputs, like how much are you going to delay, which units are you clicking on, like I don't actually see exactly where the actual output of this goes. Right, at some point you have to take an action. So like, what is that action? Okay, each of the three modalities is encoded and processed independently using a fitting architecture. Transformer for the unit, ResNet for the feature planes. This is actually kind of an older, I feel like they should have used a vision transformer. Arguments are embedded as well. We use special operations and interactions between these modalities. We scatter units into feature planes. We place the embedding of each unit in its corresponding spatial location on the feature plane. So kind of like a position embedding kind of idea where there's some feature that represents the unit, but then they also are attaching to that the information that says, okay, this is the unit, but this is also where the unit is, at least in 2D space. Feature planes embedded into vectors used strided convolutions and reshaping. The reverse operations to embed vectors into feature planes. Tried using memory, which can be a long short-term memory or a transformer XL. Most of our results do not use memory. Yeah, and part of the reason you don't want to use memory is because then when you actually perform inference, the memory is going to be a huge pain because now you have extra memory requirements. For the experiments using a value function, we had an MLP on top of the vector features to produce an estimate of the value function. Okay, I think that's this right here. So there's an MLP that takes the output of this random little MLP here and then actually calculates the value function. So I guess the gradient coming from the value function is coming in this way. Sample actions. 7 arguments are sampled in the following order. Function, delay. Okay, so these are the actions. All right. We sample actions sampled in the following order. So they call it sampled arguments instead of just actions. Why didn't they just fucking call it actions? I don't know. They called it sampled arguments. So these are all the outputs that this neural net or this system creates. That makes sense. Okay. First 4 arguments sampled, next 2 are sampled from the vector, and finally the world argument is sampled. Note that the unit tags is actually obtained by sampling a pointer network 64 times, so conceptually unit tags represent 64 arguments. Dude, what? At the train time, the MMR of the player who generated trajectory is passed as vector input. I could see that being very important, right? So if you're learning in this offline way, it's useful to know if the game that you've looked at is from a trash player or a high player, right? So there's a very small amount of high MMR data in this data set. So I think it makes sense that you would want to let the network know when it's observing a human that is trash versus a human that is has a high MMR. This is similar to return condition behavior cloning. For the mu0 detailed, we define the latent space L as the space of vectors before the function MLP. Okay, we're going to need to open a new page here so that we don't keep scrolling around. Let's do this. Let's open up this. Let's go here. Okay. Before the function MLP. So the function MLP is this one. Okay, so you have your MLP here, and then you have your function. So right before there. We split the model presented above into an encoder and two decoders. Okay. One decoder maps latent spaces to distributions over actions. Okay. So this is the one, the distribution over action is kind of the same way that you would have a distribution over tokens in a large language model. And then you can say, okay, well, which action should I take? Where is this distribution telling me the highest action is? And a value function decoder, dvpi, such that policy conditioned on state equals this decoder encoder S. So you're encoding the state, then decoding it, and that is basically the policy. Okay. Here you have the value function is basically the same idea. The value function is encoding the state and then decoding the state. Okay. Note that our implementation, the decoder actually produces distributions for the function and delay only. The other arguments are obtained from the estimated behavior policy mu. Okay, so the estimated behavior policy is trying to match the unknown behavior policy, which is the human. So you have one behavior policy, which is kind of being trained by the value function, I guess, and trying to find the most optimal action. But then you have another another policy, which is trying to match the unknown behavior policy, which is the human, which is kind of more of a behavior cloning. I'm getting a little bit confused here for sure. So if you guys are confused, let me know. We can break down into any of these areas. Add a latent model, L times A to L. Given a rollout, we compute this. So a rollout is a bunch of state action pairs. Episodes are basically the same thing. Here you have H naught equals the encoded value of S naught. HK plus 1 is this latent HK AK. Oh my god, it's getting double encode, double pass. So H naught, H is basically what comes out of these encoders. So it's basically just a vector. I don't understand a different way. Yeah, they're just kind of going hardcore in the mathematical formalism here. And then this vector here, which is the encoded state, right? So S naught is the initial state. You encode that, you get the initial latent, I guess. That initial latent isn't used anywhere here, but that latent, if you combine it with a specific action and then feed it into this L, you get HK plus 1. So I guess L is the latent space transition function. They don't say it, but that's my guess as to what that is. You have your policy is just the decoded latent here, where the latent is just the encoded version of the state. And then your value function is the decoded version of that latent. Okay. So this is just this equation here, and then this is just this equation here, but they've replaced HK or E of S with HK, and here you see E of S has also been replaced with HK. Note that S0 is only the first state, but not necessarily the first state of an episode. Okay, so here they're kind of drawing a distinction between an episode and a rollout. So a rollout is can be a chunk of an episode. The episode is the actual full game. The rollout is maybe 20 seconds of a game or something like that. Illustration of the architecture used for mu0. E is the encoder, L is the latent model, and dpi and dvpi are the policy and value function decoders. So E is the encoder. Your states are being fed into this encoder. That encoder is encoding them into some latent. That latent is being given into this latent model. The latent model takes the latent of the current state as well as the current action, and then I guess produces the next state. So this L is basically attempting to mimic, or this L is over time learning how the latents change according to an action. So you can envision a function that takes in a state at time k and an action at time k and produces the state at time k plus 1, right? It says, if I'm in this current state of a game and I take this action, here's what the state of the game is going to look like. So this L is doing that exact same thing, but it's doing it in latent space. So rather than predicting the next state, it's predicting the next latent or the next encoded version of that state. So if your state is huge, which we've learned up here, right, there's all this extra crap in the state. There's like all these different maps, each of them 128 by 128, all the different parts of all the different units, all the different metadata associated with the current state of the game. That's a whole lot more crap than just one latent vector that says, here's the current state of the game. So that's why it's easier to do this, to build this world model, right, in with latents. So that's what this L is. Then you have decoders, and your decoders are taking that latent state and they're decoding it into either the value function, which is trying to predict the reward, which is basically, am I going to win this game or not? Or the policy, which is what decides what action to take. So that's why there's two different decoders there. Behavior cloning. Our first reference agent is trained using behavior cloning, which is just mimicking what the human does. Assume what the human does is perfect. The process of estimating the behavior policy. We learned an estimate mu hat by minimizing the negative log likelihood of the action t under the policy. Okay, so basically they're trying to match the human policy, which I think is mu hat, right? The unknown human policy. And here you have the loss for behavior cloning is the summation of the log probability of the human taking that action t in that state t, given that state t, and you're summing that from time equals 0 all the way to the length of s, which is the rollout, the length of the rollout, yeah. However many steps there are in that rollout, I guess. And then your loss, you want to minimize the loss, so you put a negative there. Because you basically want to maximize the probability that your action is the same as the human action, which is the same as minimizing the negative probability. Since each action is comprised of 7 arguments, there's only 1 loss per argument. In order to avoid overfitting, we use a weight decay loss, which is defined as the sum of the square of the network parameters. Okay, so they also have weight decay, which is slowly eroding the value of these network parameters. Behavior cloning mimics the training data, so higher quality data should lead to better performance. Yes, if you're going to do behavior cloning, you definitely want to train on only the good games. In order to get the best of both worlds, we use a method called fine-tuning. It is secondary training phase after running behavior cloning on the whole dataset. Okay, so basically for this behavior cloning agent, they train it on the whole dataset first, and then they fine-tune it on only the pro gamers. Offline actor critic. Actor critic algorithms, look how ancient. Bartow, 1983, Witten, 1977. These are fucking ancient RL. Learn a target policy pi and the value function v of pi. So you're learning 2 different neural nets here. In an off-policy setting, where the target policy pi differs from the behavior policy mu, we compute importance sampling ratios. Okay, so you're going to be sampling from all your offline data, and you need to know, okay, well, what things should I sample from versus other things? You probably want to sample from high-quality actions in high-quality games. You probably don't want to be sampling a bunch of state action pairs from a super low MMR game where nothing happened, right? So coming up with some form of importance, which is like, how important is this particular state and action to actually learning what I want to learn? That's where you're going to get this importance sampling. There are many different variants of the loss in the literature. The simplest version is called one-step temporal difference, or TD learning. So here you have the discounted reward, the discounted sum, but here note how the discount is no longer the reward, but the value function. So now you're using the value function to learn the policy. So the policy can either learn from the value function, which is estimating the reward, which is estimating whether or not you're going to win or lose, or the value function can learn to mimic the human, which is what this behavior cloning is. So two different types of reinforcement learning here: behavior cloning and then offline actor critic. VPI is called the critic. The loss can be modified to use n-step temporal differences by adding more terms, blah, blah, blah. Learn the estimated by minimizing the mean squared error. Okay, so you learn the value function by just an MSE loss over the reward. This is the 1 or a 0 at the end of the game, and you're trying to learn the value function at every state based on that with this loss here. And then this is the TD learning is used for the policy. So this is what you would use to learn the policy. This is what you're going to use to learn the value function. Although actor critic has an off-policy correction term, it is not enough to make it work without adjustments. The behavior policy appears in the denominator, but we do not have access to the behavior policy use, so we can only observe. The behavior cloning learns an estimate, which we use to compute the estimated. Interesting. Okay, so in order to do this importance sampling, which they talk about up here, they need to know what action the human would take, or the probability at this current state. What does the distribution over actions look for the human policy? But they don't know that. So actually what they're going to do is they're going to pretend that their behavior cloning agent is a human, and they're going to say, okay, well, behavior cloning agent, which learned to mimic the human, come over here, look at this current state. What action would you take? Or what is your probability over all these actions? And then they use that as kind of a proxy of what the human would do, which is kind of, this is clever, but it's also, you're introducing a little bit of weirdness there. Standard and actor critic, this can be done even in offline settings. Leads to a divergence during offline training, which is known problem. Unfortunately, leads to a divergence. As soon as you go too far away from states and actions that you've seen before in your offline data, you have a problem. Improves first before deteriorating, therefore it could stop training. However, this method requires running the environment to detect where to stop, which is contrary to the rules of AlphaStar. Instead, we use vmu as a critic and keep it fixed. Okay, so the value function for the human policy instead of the value function. I don't know what this means. I think this is sometimes called the dagger problem. The deadly triad. No, but basically the intuition that they're talking about is that these reinforcement learning systems are very sensitive to the areas of state space, of state action space that they've explored, right? So if you take very weird actions playing StarCraft against one of these agents, it's not going to know what the fuck to do because it's never seen that before. So they only work well within the distribution that they've been trained on, which is property of kind of all learning systems, is that they are very good at interpolating, but they're not as good at extrapolating. So if you guys ever want to know how to prevent the Terminator from killing you, it's just do something so weird that it's never seen before, and it'll be confused, and then it won't be able to kill you or maybe you'll have a split second to run away. Mu0. Mu0 unplugs, adapts a Monte Carlo tree search to the offline setting. This is basically just brute forcing your way through possible moves. In order to handle large action space, we sample multiple actions from the policy and restrict the search to these actions only. Okay, so there's some distribution over all actions, and here they're going to sample maybe the top 10 or something like that, and then restrict the Monte Carlo tree search to only those top 10. The latent model presented in section 4.2, similarly, we only improve the function delay. Mu0 supervised. Training the target policy and the estimated value function jointly can diverge. Right, so if you're training this policy based on what the value function is giving you, it's kind of a multiple steps which can add more crap and noise and divergence. This results in only using the losses for the policy and the value function. Behavior cloning performance with different mini batch sizes M. So this is the actual size of the batch that you're feeding to the policy, which is trying to mimic the human, right? So the behavior cloning one is the one that mimics the human. And here, this is different amounts of data. Rollout length. So you're feeding it a batch of 8,000, but each rollout, right, is basically just one step. So here at this step, I took this action, and that's where I ended up. Versus this, I think, is a much more interesting mini batch of data where you have 256 different step actions, but they're step action, step action, step action, step action, or state action, state action, state action, and there's 64 lengths. So it's a sequence of 64 rather than 8,000 random state actions. But actually, this is actually super cool. Look at this. I would have thought that this one would have performed the best, right? Because you have that notion of kind of a trajectory of a sequence. There's actually a meaning to the sequence in the mini batch. But here, 32,000, just this absolutely massive mini batch of just single individual little rollouts where each rollout is just one step gives you the highest win rate by like 5 points here, 5%. So that's definitely not intuitive there. I would have thought that this one would have been the best. Policy and value function are computed using the latent model for all steps except the first one, although the loss is similar to standard. And this is another reason why they do this, right? So we saw here how they were basically doing everything in this latent space, right? They're not actually using the state. They're almost always taking the state and encoding it into this representation of the state. And why would they do that, right? Like, well, one of the reasons why they would do that is because the computer that's running the StarCraft simulation is different from the computer that's actually training, right? And actually has the little policy neural net or the little value function neural net. It's actually pushing gradients. And imagine if you had to communicate the entire state between those two computers. That would be so much more annoying and computationally intensive than just having the computer that's running the StarCraft. It gets the state, it compresses the state into that little latent vector, and then that's what it sends. So the little computer that's running StarCraft only has to send out those little latent vectors, and the computers that are actually training only have to receive little latent vectors. So compressing the entire world of StarCraft into this little latent vector that represents the state is not just kind of a trick for weird theoretical reasons. It's a trick because it's saving you a ton of compute over time, a ton of overhead and communication overhead. Using this method can lead to improved performance. Mu0 with supervised Monte Carlo tree search at inference time. So that's what MZS-MCTS stands for. Mu0 supervised Monte Carlo tree search agent. Policy improvement and training can lead to divergence. Using MCTS, on the other hand, is stable and leads to better policies. Okay. We measure the influence of several parameters. For simplicity, we use the win rate against the very hard bot as the metric for these experiments. Okay, so this is what we saw before. They're going to basically play this AI agent against the very hard bot and then see what happens. Mini batch size M and rollout size K influence the final performance of the models. This is what we saw in this table here, which was kind of interesting how a rollout of size 1 with a huge mini batch ends up being the most important. Found that more data per step, the better the final performance. So kind of goes with the intuition that I generally talk about on this channel, where the bigger your batch size, the better your gradient step, right? The bigger your batch size, the way I think of it is the step that you're going to take as a result of that batch size is going to put you in the right direction way more than a small batch. A small batch is going to be a much more noisy trajectory through that hilly landscape. Is rollout length equal to 1, similar to next token prediction in LLM? Maybe that, not quite. So think about it as if you were doing a batch of data for a language model. It's going to be hard because the analogy doesn't quite work here, but let's say that in your batch of data you had 10 sentences, right? Or 10 sentences from 10 different books, and you needed to predict the next word in each of those 10 sentences from 10 different books, right? So think about if your batch that you were feeding into your language model, there was 10 in there, and each one of those was basically independent. Versus if you had a batch of 10 and you basically had to predict the first word, and then the second word, and then the third word, and then the fourth word, and then the fifth word. So LLMs don't actually work like that, but the intuition is more that at a k equals 1, it means that everything in your mini batch is basically like some random snapshot of a single frame of some unrelated StarCraft game. So it's 32,000 random snapshots of unrelated games, versus in the mini batch size of 256 with a rollout length of k, it means it's 256 snapshots of 64 steps. So maybe 64 steps is like 3 seconds of total game time, right? But each of those 64 actions is related to the other ones, right? So like action 64 is related to action 63, is related to action 62. So in this mini batch here, there's a little bit more similarity between the data in that mini batch, right? Because a bunch of them come from the same rollouts. There's only 256 possible rollouts. But in this one here, it's all unrelated. It's just like you have every single individual piece is just part of a rollout of length 1, which means that it's only just one snapshot. Does that kind of make sense, Ed? I'm sorry if that doesn't make sense. Okay, but largely what they're kind of finding is that you basically increase the batch size, you get better training. Comparison of learning rate schedules. Okay, so learning rate schedules are ways of changing the learning rate, scheduling it over the course of training. Usually you're trying to make it smaller over time, but there's other fancier learning rate schedules. Here you have a cosine schedule versus a constant schedule. Constant schedule would just be keeping the learning rate the same, and you can see how the learn rate or the cosine learning rate schedule does lead to slightly better performance. And final performance for different initial learning rates. So here they're starting with a small learning rate or a big learning rate. And you can see how the small learning rate takes longer to learn, right? And it also is shittier. Versus this one here, slightly larger learning rate, performs better. But then the interesting part here is that this one here, 10 to the negative 3, which is even bigger than this learning rate, performs worse, right? So why does the green one perform worse than the orange one? And I think to build that intuition, we need to look at the gradient descent neural nets. Image, ball on hill. Yeah, this one. So when you're performing gradient steps, the analogy I always think in my head is that you're basically rolling this marble on a hill and you're trying to find the minimum, right? So the learning rate is basically the length of your steps. So a big learning rate means you're taking big steps, but a small learning rate means you're taking very little small steps. So if you just want to get to the bottom of the hill, wouldn't just big steps be the way to go and you just get to the hill faster? And the answer is like, not really, because sometimes the minimum you actually want is very precise and small. And if you're just sloshing around with these big 10 to the negative 3 learning steps, you're not getting anywhere. You're just kind of like taking big random steps and like you're not finding that little fine area that you actually need to get to. And that's why this learning rate is actually better, even though it's smaller than this learning rate. Okay, so that's a little bit of intuition there. Learning rate has a significant influence on the final performance of the agents, which is not good. Like, another intuition that I think of is when the learning rate matters a lot for the final performance, what that's telling you is that you're kind of relying on luck. You know, if your optimization was properly constrained and your optimization was set up in the right way, then a bigger learning rate should get you to the final answer faster, right? But if you have to be fucking around with the learning rate, that means that your optimization is set up in such a way that you're not actually getting to the final. Your optimization doesn't lead you to the right place, and basically you have to kind of get lucky in a sense and just kind of be walking through this landscape, and then you just randomly fall into this pit that ends up being much lower than you thought it was going to be. So I don't know, just some random shitty intuition there for you guys. Dance off? Me doing this? Okay, so here we have the learning rate is the minimum of k over this. Here's your cosine. So this is a cosine learning rate here. And there's some frequency here. Kmax is the total number of training frames. We compared this schedule to a constant learning rate. Different mini batch sizes. It's common to look at the win rate before the experiment is over. It's noteworthy to mention that should be avoided to find the optimal lambda knot. Yeah, it's only the best performance is obtained with the 10 to the negative 3, but after the full training, it changes. This seems wrong. The best performance is not obtained with 10 to the negative 3. The green is not above the orange. I don't know what they're talking about. Learning rate schedule is used to train the reference agents as detailed. Okay, number of training frames. Trained most of our agents over Kmax 10 to the 10th input frames. Okay, so fine-tuned, behavior cloning fine-tuned, and then offline actor critic and E offline actor critic. I don't know what E offline actor critic is. Restarting from the behavior cloning agent. Okay, so now they're starting to get complicated, right? So we've had, at the beginning of the paper, we established these kind of two basic ways of doing it. Either behavior cloning, where you're just trying to match the human, or actor critic, where the critic is trying to predict the reward and then the actor is trying to basically please the critic. So now they're going to make things a little bit more complicated by bootstrapping and initializing each other on the thing. So here it sounds like they might train the offline actor critic on episodes collected by the behavior cloning agent, or we saw how they were using the behavior cloning agent in order to get the importance sampling used for the offline actor critic. So they're starting to like mix and match on these different approaches here. Performance when varying the number of training input frames. Number of training frames. Okay, so roughly the more training frames, which is basically how much data you have, the better your win rate. That kind of makes sense. Dataset size and number of episodes. Okay, also kind of increasing. Also makes sense. MMR, win-loss, filter episodes, fine-tuning, win rate versus very hard. What do they mean here? Filter, win. Okay, so here they're only training on... Oh, okay, so here's what's going on. So here they train on an MMR greater than 3,500, so only people who are medium good, games where it was like a medium player versus a medium player, they're training on the wins and the losses, huge amount of them, and they get 84%. Compare that to training on only the very, very good games, so games that are above 6,000, train on both the wins and the losses, but way less data, right? Because there's way less players at that MMR. Get way worse of a score. So already that's giving you an intuition here where it's worth training on shittier games if you have way more shittier games than really good games. So the data set size is more important than the quality of the games being played. And here they show you, okay, if you only train on the wins at 6,000, you get even worse. So it's worth training on the losses, right? That's also important. And then the final row on this table here, it says, okay, greater than 3,500, training on both wins and losses. So it's basically starting from 84%, but then we're also going to fine tune it for only on the wins of above 62,000. So the best possible games, the 21,000 best possible games, we're going to fine tune on that, and that's where you get that 89%. So they should have ordered these a little bit differently. I would have done the 51%, then the 65%, then the 84%, then the 89%. But this is actually a very nice table because it shows you how the data quality makes a difference. It shows you how the data set size makes a difference. And then it shows you how you can go from only kind of one step, right, where you're only training versus this kind of two-step main training and then fine-tuning. And that's how you get the final performance of 89%, which is pretty good. I love this table. This is my favorite table of this paper right now. Shows the behavior cloning performance for different sizes, number of uniques, blah, blah, blah. The win rate with only 10% is close to the best one. Can be used to save storage at very little cost if it is a concern. Further reducing dataset size significantly alters performance. Data filtering. Okay, so I guess that's basically just the table we're looking at. And then table 3 here, we got comparison of behavior cloning against a very hard built-in bot with different implementations of memory. Okay, so the memory here, memory is a very overloaded term. It means like 17 million different things. You, of course, have memory in your computer, but here they're referring to the memory of the game, of the system itself. So, for example, here, right, you have this policy and this value function, and they're receiving this latent here, and there's what is this arrow here? This arrow is coming from the past, right? So there's an arrow coming from the past here saying, oh, here's the latent of the previous step. So that's a form of memory. And here's another form of memory right here, previous vector arguments, previous unit arguments. So you have information from the past coming in, and you can store that information and then give it to the next step, right? And RNNs and LSTMs are basically based around this fundamental principle of like there's some calculation or compute you did in a previous step, give me a little bit of that compute and a little bit of that calculation, right? Give me a little something. Give me a little something that tells me about what you did in the previous inference step. LSTMs are doing that in a much more clever way where they're kind of like they have these gates and they're basically toggling whether something is getting stored in the long term or short term memory, but it's like it's the same kind of idea of like there's some compute that you already did previously, give me a little bit of that compute or some latent or some embedding that allows me to understand what happened. So here they're comparing LSTM versus no memory, and interestingly, no memory wins, which is kind of crazy. You're better off not knowing what the fuck you did last step than knowing what you did, or at least with the LSTM. A transformer is not like an LSTM in the sense that it's passing something to the next step. The transformer looks at just the entire thing all at once, right? So here in the transformer, what they mean is that basically you have the entire sequence available for you. So you have all the steps previously, and the transformer, right, has that attention mechanism where it's basically saying here's the sequence and then here's the sequence. So maybe one way to think about it is the LSTM tells you maybe what the previous word was. If you're thinking in a sentence, it'll tell you here's the previous word and then here's fragments of a word from 10 steps ago. Versus the transformer is here's all previous 10 words that I gave you. And of course, you don't need to read a reinforcement learning paper to understand that transformers ended up being way better at next token prediction, which is kind of a proxy for this, right? So the fact that LSTMs here perform very well for this StarCraft win rate versus Transformers makes sense in the context of, hey, we've figured out that Transformers are way better at sentences and language than LSTMs, which is what people used to use for natural language. Performance, memory less, blah, 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 performance. Transformers require extensive hyperparameter tuning and longer training times. Therefore, all of our agents are memoryless. What? They haven't even touched it? That's fucking stupid. You didn't even use a transformer. That's lame. Super lame. All right, let's keep going. Because of the complexity of the model, many parts could be scaled individually, but this would be prohibitive. Aren't you DeepMind? Like, don't you have monster compute? Like, I want to see massive wasted compute. Our standard model size is the largest model which can fit in memory without significant slowdown. That's basically how anybody does that. Blah, blah, blah. During inference, we sample from the policy. Sample from the policy given a state S of t. That's just like a super fancy way of saying we take an action. This policy, which is a neural net, it'll consume the state, or in fact, it's consuming the encoded state, and then it's outputting action. Here's what I'm going to do. In praxis, the policy is characterized by a logit vector y, right? So here you have temperature. So temperature is a common parameter that you see in language models. So when you're performing inference with a language model, maybe you're using OpenAI's API, and there's this little number there that says, what's the temperature? So what the temperature is it's changing basically the probability distribution over all the tokens. So it's not, so you can see how if the logits are YA, that's actually the raw probability, even though it's not actually a probability, but it's like the raw information that's coming out of that neural net. And then you're putting that into a softmax function to turn it into a number between 0 and 1 so that you can actually interpret it as a probability. But the softmax function, which is this right here, exponent of that thing over the sum of the exponent of that thing, if you divide it by this temperature, you can change the shape of the softmax, which then ends up changing the numbers that come out, which you're interpreting as a probability distribution. So softmax temperature explained. There's one GIF that I remember showing that is like the best GIF ever. I think it's this one. No. Let's see if I can find it. Roll of temperature. No. Temperature explained. I'm telling you guys, it's worth the is it this one? Yeah, here we go. This is the GIF. So here is the probability distribution. Get the fuck out of here. You have softmax without temperature. So this is your softmax equation. Here's the softmax with temperature. You see how we've added this over t. Here they're just using beta as the softmax, right? But you can see how when you don't have this temperature, here you're doing classification over 9 things. Maybe your next token, your vocabulary, there's only 9 possible or 10 possible tokens that it can be. And your model is telling you this is probably the token that you want, right? This one here, this one that has the high number. If you increase the temperature, you could think of this as less entropy, more entropy, but I think that just makes it more confusing. What you're really doing is you're basically making that softmax, temperature in softmax. There's another image, temperature in softmax. Where is it? Where is it? Maybe this? No, that's not it. This, here. You see this? See this? This is the surf softmax curve, and you can see how as you increase the temperature, you change kind of the pitch of that softmax. So it's becoming more and more pitched, and the more and more kind of like pitched like that it becomes, the more that whenever you feed numbers into the softmax, right, and the softmax is taking a number from negative infinity to infinity and turning it into a 0 and 1, the more pitched that is, the more those numbers are basically going to be closer and more similar. And that similarity looks like this, right? So now, rather than it being very obvious that you have you should pick number 9 as your next token. Now it becomes a little bit less obvious because some of these other ones are, oh, these kind of look like good candidates, you know? Maybe 9 is not the answer, right? And that's why when you increase the temperature in a language model, what you're doing is you're basically making it more likely to pick other tokens that aren't necessarily the best token. So you're making it more random in that sense. So I don't know, that's my digression on temperature. But here they're changing the temperature for sampling the policy, which is an action. So rather than next tokens, or rather than a probability distribution over tokens, the policy is a probability distribution over all actions that it can take, all possible actions. And here you're changing the randomness with this temperature. I can't even keep up with my own arguments, so I don't know how the fuck you guys do it. Beta equals 0.8 is a good value for the temperature during inference. Okay, good to know. Temperature during divergence, behavior cloning, fine-tuning, offline actor critic, emphatic offline actor critic. So now we finally know what EOA is, EOAC. But it does seem like there's a little bit of a difference of temperature here. Win rate against the very hard bot. This is actually something else. Let's stay here. So it does seem like you want a little bit of randomness, which is, or not a little bit of randomness, you want a little bit more certainty. So lower temperature, higher score. I kind of like this. Like, I like how all the tables in this paper give you a single metric. You know, so they decided, okay, at the very end of the day, the only thing you give a shit about is how much is this agent winning against the very hard bot in StarCraft? How many times, what percent of games when it plays against the standard AI that Blizzard designed, does it win? So I like how all the tables in this paper, they don't give you like weird metrics that are difficult to interpret and like a table with 500 different columns that represent all these different metrics. They just give you one metric. And this just makes these so much easier to interpret, right? Because then I can just go, oh, 90%, 95%. I know exactly what that means. Very easy for me to understand. So props to whoever decided to do that. That's a big win. Win rate against the very hard bot for offline actor critic training. So fixed value versus train. So this is the value function. Whether or not you're using one or the other, win rate. And it seems like there's some kind of weird, like, pathology happening here. Like, something happens to this value function here where eventually it just basically dies. It, like, kind of, like, stops being good and then eventually collapses. So that's not good. Clipped importance sampling over training. So you have your importance sampling, which is telling you how important one rollout is versus another, and then you're also clipping the importance of that. Okay, and I guess what they're showing you here is that the blue one, which is the fixed value, it doesn't fail. So the blue one here, right, you see how the part here that's gray, that actually represents the blue, and it's telling you the variance. So it's telling you if you try this with a bunch of random seeds, you would end up getting something over here, right? Versus if you tried this with a bunch of random seeds, you would sometimes end up over here. So the fact that they're close here isn't the whole story, right? Because you also want to account for the variance, and the variance is definitely way worse for this orange one than it is for this blue one. Critic of offline actor critic. We experimented using the value function of the target policy as the critic instead of using the fixed value function of the behavior policy. Okay, so different value functions, playing with these value functions. One comes from the behavior cloning, one comes from the offline actor critic. Although the win rate first increases, it stays high. Importance sampling decayed much faster and lower when using the one that's learned through the offline actor critic. Preliminary experiments were not successful. There almost never are. You know, this is another thing about machine learning. It's like it pretty much never works until the very last moment, and then it works. It's a very stressful area to work in and do research in, because like it doesn't work, and then it works. So maybe similar to coding in that sense, but yeah, it's It's not fun. Policy collapses quickly. So collapses quickly to a few actions means that the policy stops giving you good actions, and basically what it ends up doing is it just ends up saying, click here, click here, click here, and it always gives you the same few actions. To investigate and evaluated the performance of repeated applications of Monte Carlo tree search policy improvement on the behavior policy. We do this by training a new mu0 using MCTS actions on the behavior policy, and we found that MCTS performance is worse than the performance of VHAT. Repeated applications of Monte Carlo tree search do not continue to improve the policy. Good to know, because Monte Carlo tree search is trash, because you're literally searching through the state action space explicitly. 6 reference using 3 metrics, robustness, elo, and win rate. This is the one that we've been looking at the whole time, this win rate versus very hard built-in bot. Metrics are explained. The 3 best agents utilize offline RL algorithms. Okay, so what do we got here? Win rate matrix for reference agents. So here we have the different agents. So you have behavior cloning, you have offline actor critic, you have emphatic offline actor critic, you have fine-tuned behavior cloning, you have mu0 S, and then you just have the very hard. So very hard bot against very hard bot should basically win 50% of the time, which is what we see here, right? So if the very hard bot plays itself, it should win about 50% of the time, which makes sense. If we have the behavior cloning agent against the very hard, wins about 11%, versus the fine-tuned behavior cloning against the very hard. Actually, I think I'm reading this opposite. This is the 90% and this is the 95%. I think who's winning in this situation? Which one wins? Is this the very hard bot wins 5%, or is this the fine-tuned behavior cloning wins 5%? I don't think this is the case. The win rates do not always sum to 100. Okay, so these are the worst here. mu0 Monte Carlo tree search, 4. No, very hard is the worst. Okay. So the rough color of each row here is going to tell you how strong it is. So this is the strongest one. MZS, MCTS, mu0 Monte Carlo tree search is the strongest. And then the weakest is the very hard AI that Blizzard created. And then behavior cloning is below fine-tuned behavior cloning. This makes more sense. And here you have your 88 and your 94. Okay, so this finally makes sense. These are basically ranked from shittiest AI to best AI. And I wouldn't even count this bottom one as AI. This is like hard-coded logic created by some game designer at Blizzard. We observe that mu0 supervised with MCTS at inference time, reference agent performs the best at the cost of slower in inference, right? And why is it slower in inference? It's because it's doing this Monte Carlo tree search, which means it's kind of like looking ahead and saying, okay, well, if I were to take this action, what would that look like? And then what action could I take after that? So that's this kind of like tree search, right? It's like searching forward in time at each possible action. And you're kind of doing this in your head too, right? So like whenever humans play chess, I think I don't know much about chess, I'll just be honest, but I think that they're kind of doing a version of that, right? Where they're thinking moves ahead. They're like, okay, if I were to do this, then where would I end up? And then what things would they do? And then what things would I do? And so on. Okay, we compare with the original AlphaStar. The AlphaStar Supervised was trained as a 3 race-specific agents. Okay, so you have 1 specific agent for each Protoss, Zerg, and Terran. Therefore, we also compare agents to an AlphaStar Supervised. So AlphaStar Supervised, I guess, is a previous work where they just basically behavior cloned to race-specific agents. Train on several orders of magnitude more computing power. 6 reference agents with the proposed metrics. the bottom portion, we show the performance of tables from this 2019 paper. Our behavior cloning agent is most comparable to AlphaStar Supervised, but performs better due to significant tuning improvements. Highlighted in gray. This is like, I wish they told us what those were. You know, it's all the bag of tricks that DeepMind has. Win rate versus 95%. Offline actor critic 98%. It's kind of weird. Why is this higher than this? I guess it is higher. So this number is higher than this number. Yeah, okay, so maybe it wasn't ranked as I thought. Race-specific networks with fine-tuning plus online learning. Race-specific networks plus fine-tuning. 100% win rate against very hard. Damn, that's got to be hard. This is 2968. But this is online learning. So not only is it 3 different networks each for each race, but then you also have fine-tuning and you're also learning online. The online learning means that it's playing itself basically, or it can play the very hard bot just over and over and over again, so it actually can explore more effectively, right? One of the biggest problems with off-policy RL or offline RL is that it has a hard time going off policy, which means that it's basically an exploration problem. It just hasn't seen a lot of action and state action pairs. Okay, so here you have more offline baselines that they're going to basically just plug in so that you can compare to a bunch of historical RL algorithms such as PPO, which is actually, I think, what they use for the fucking RLHF on language models. They use PPO, which is actually quite old and shitty at this point. Imagine if they used one of these RL algorithms. And that's why I'm so excited about the Gemini. Like, that's why I feel like it's going to be crazy, because they've definitely wrapped it. So if I was working there, what would I be doing? I feel like I would take these language models and I would have them play a debate. So like a debate game where they just talk to each other and they have access to different books and different information, and they can prepare a debate and then they debate each other, and then there's different LLMs that maybe judge their performance on the debate. And create this simulation, this environment that can be perfectly simulated, such as a debate game in which you have LLMs play each other, and then take that game and just blast it with one of these RL algorithms that does self-play. Right? Gemini. DeepMind. Gemini is artificial superintelligence. Gemini that works on text is being developed. So it doesn't exist yet. It's being developed, and it's basically the DeepMind. It will eclipse ChatGPT. They're basically going to take ChatGPT, which is a language model that just predicts the next token, right? Plus a little bit of RL, but the RL that they added to ChatGPT is quite minimal. And then they're gonna put it in. They're going to put it in a simulated game, and then they're going to make it play itself. And I think it's going to be some kind of debating game or something like that. So it has to be entirely text-based, but I don't think they're lying here with the will eclipse. I think it's going to be absolutely insane. Like the language model that they're going to get from doing this, especially if they play some kind of debate game or some kind of 21 questions or any one of these text-based games where you kind of like are trying to deceive and trick the other person with text. Like, people are not ready for this. This language model is going to be so good. It's going to know exactly the questions to ask, and it's going to be playing this like 500 IQ wordplay game, and you're not even going to be aware of it, right? The same way that the Go, right? The Go agent that we got the best human to play, right? What is it? What was his name? Go versus human or something. Lee Sedol, right? So DeepMind created AlphaGo, which is basically this, right? It's an online reinforcement learning self-play, and they got it to play the best human player, and it beat him, and it beat him in like a weird alien way. Like, there was specific moves that it did that were just like fucking weird, and like we didn't understand as a human. So think about that, but rather than playing Go, it's now going to play text. It's going to just do some kind of debate, some kind of weird text game, and it's going to be extremely good at that text game, and then they're going to take that and just probably give it to you. And that AI is just going to be, I don't know what it's going to do. It's just going to destroy us probably. It is Skynet. Okay. Trained offline Q learning agents based on DQN. This is Deep Q networks. This is one of the first reinforcement learning with deep learning papers. Offline RL methods. We trained a bunch more RL papers. Bunch more RL papers. Okay, so they're basically adding a bunch of different RL implementations as baselines, which sounds like they're doing a lot of work, but they already did all this work. So all of these older RL algorithms, they're all implemented, so all they had to do was basically just plug it into this benchmark. Behavior cloning is the foundation of all agents, and does this work? Yes, because even the offline even the actor critic ones are using the behavior cloning value function. The offline RL agents start by estimating the behavior policy, using behavior policy, then using behavior cloning, and then improve upon it using the reward signal. This allows them to perform significantly better than the behavior cloning results. Yeah, so this kind of two-step process of use behavior cloning to bootstrap your actor critic. Indeed, although the agents are conditioned on the MMR during training, the behavior cloning agents are still fundamentally limited to estimating the behavior policy, ignorant about rewards, right? So behavior cloning, they're just trying to mimic the human, even if the human does stupid things. The policy then learns a smooth version of all the policies. In contrast, offline RL methods use rewards to improve learned policies in different ways. Offline actor critic methods use policy gradient. This is PPO, proximal policy gradient. The gradient is coming from the value function. That gradient is being used to improve the policy, so the actor is receiving gradients from the critic, basically. Very similar to generative adversarial networks, where you have a generator and a discriminator, where the generator is receiving gradients from the discriminator. So it's actually a very good analogy of GANs and actor critics, where basically you have two networks kind of playing opposite sides of this game, where the critic is kind of like the discriminator and the generator is kind of like the actor. Obviously, there's differences, and if you guys want to be sticklers, there's differences between GANs and actor critic, but I think there's more similarities than there are differences. Maximizing the estimated return. Even the mu0 supervised without MCTS and Monte Carlo tree search and the fine-tuned behavior cloning make use of that reward and outperform the BC baseline. We have observed that algorithms originally designed for online learning, even with off-policy corrections, do not work well when applied directly to full offline RL settings. Yeah, I could have told you that. We attribute this in part to the deadly triad. Many recent works have found these algorithms can be made more effective simply by making modifications that ensure target policies always stay close to the behavior policy. So this is the idea that if you wander too far off the path of things you've seen, you're going to perform very poorly. So if you're doing offline reinforcement learning, you either need the offline data to be exhaustive and kind of basically every possible state and action pair that exists, which usually is only possible in very constrained environments like chess and Go or Atari games, but is a lot harder to do in even a game like StarCraft, where you could theoretically create an exhaustive list of state action pairs for StarCraft, but you could not do that for the real world. It's literally impossible for the real world. Our results with Actor Critic and mu0 are in accordance with these findings. Amongst all the methods we tried, the reference agents are the ones which led to improved performance. However, we tried several other methods. We have failed to find the modifications. AlphaStar Unplugged is fundamentally difficult. Limited coverage. Okay, so action space is very large. State action coverage is low. So even though they have all these games, there's still a bunch of weird stuff that they've never seen. Extrapolating to unseen state and actions, generalizing outside of the training distribution is difficult. Particularly impactful for Q values-based methods. So values or methods that are trying to estimate this Q function. This RL discussion is money. I appreciate it, Joseph, but it seems like you have too much money. You should be buying H100s with that money. But I appreciate it. It is easier to learn state value functions. The approaches like R, BVE mitigate extrapolation errors during training, but still the agent has to extrapolate during inference. Weak learning signal. The win-loss reward is a weak learning signal to learn good policy games because the dataset has a wide range of qualities and the win-loss reward ignores this. Yeah, so weak learning signal or sparse learning signal would be another way to describe it, where you basically just have 13,000 steps and at the very end you have a 1 or a 0, so hard to extract meaningful signal from that. The winner of a game between two low-skilled players would consistently lose to the loser of a game between two professional players. Yeah, so if you're looking at a bunch of low MMR games, the actions that the person who won takes are probably not necessarily the actions you want to take, right? And then in a game between two professional players, the one that lost, all those little individual actions were probably all pretty good. You know, it's definitely way better. So there's kind of like this weirdness there where the win and the loss is not indicative of the quality of the actions taken during that episode. Difficult due to large action space, sparse reward, long horizon, and partial observability. Credit assignment is the idea of I can assign credit to this specific action at this specific state, right? You want to be able to say, okay, I won because of this particular thing that I did over here, right? So the longer that the game is, the harder it is to say what were the moves that actually caused you to win, and then it gets even harder with sparse rewards, and it gets even harder with the fact that it's partially observable. Autoregressive action space requires learning autoregressive Q values, which is challenging and understudied. In this paper, we wide-step us by just learning a Q function only for the function argument. So this is a value function. Okay, and then finally they hit you with the related work. They're just going to reference all their other papers here. StarCraft, Atari. Offline RL shown promising results on Atari recently, but I just don't feel like that's meaningful at all. They have not been previously applied on complex, partially observable games. Suite of benchmarks with a diverse set of tasks. D4RL. Can I get all the D's in this? Is deep, distributed, something, reinforcement learning. Let me see if I can get it. D4RL. No, it's not. It's data sets for deep data-driven reinforcement learning. Deep data-driven data set. So that's what the 4Ds stand for. RL Unplugged introduces a suite of benchmarks with a diverse set of task domains with a unified API and evaluation protocol. Has become an active research area. I don't know about has become. I feel like it's been an active research area. It was the only active research area back in the day when the computers sucked and you couldn't actually do online. Policy constraint approaches, value-based approaches, model-based approaches, adaptations of standard off-policy RL methods, and recent methods use only one step of policy improvement. Okay. Cool. We're almost there. We're almost to the end here. Conclusions. Offline RL has enabled the deployment of RL ideas to the real world. Academic interest in this area has grown and several benchmarks have been proposed. However, because relatively small and synthetic nature of these benchmarks, they don't capture the challenges of real-world offline RL. What? StarCraft isn't real life. It's not real life. I'm sorry. StarCraft is just as synthetic as other benchmarks. It's better than Atari. It's better than chess, but it's still not the real world, and I think it's important to realize that. We introduced AlphaStar Unplugged, a benchmark to evaluate agents which plays StarCraft 2 from learning by only offline data, comprised of over 1 million games, mostly played by amateur players. Thus, the benchmark more accurately captures the challenges where an agent must learn from log data generated by a diverse group of weak experts, and where the data doesn't exhaust the full state in action space. At some point, someone's going to take every single sports game, so let's say something like basketball, right? They're going to take every single basketball game ever played. They're going to run it through a pose detection model, right? Like this. They're going to get a perfect trajectory for every single player in that game. And then they're going to do a offline reinforcement learning system to figure out what the perfect basketball action is at any given moment in time. And then people will create a VR game where you can put on the VR headset and it'll put you in a fake basketball simulation, and it'll show you the exact movement of the arm and the leg and the feet and your head and the exact movement you need to be the superhuman basketball player. And eventually all sports will become like this, where you are no longer learning from a human who's giving you a little tips here and there. You're now learning based on what a reinforcement learning agent has learned from observing a huge amount of offline data. And I think that this is already the case in chess, right? Now, chess has existed for some time now where AI is better than the human. So because the AI is better than the human at chess, I think a lot of the pro chess players just, they sit there and they observe these AI systems. So like for any situation, they'll be like, okay, well, what would the AI do? And then they learn from that. So yeah, it's going to be everything, every single sport, every single competitive thing. It'll stop being a thing where I come up with the plan and I learn to do things and there's a human that's teaching me how to do things. It basically becomes, here's what the AGI does, or here's what the superintelligence does for this particular game, and I'm just going to mimic that. How's it going, Jin? We show that offline algorithms can exceed 90% win rate against the all-races version of the previously published AlphaStar supervised agent. However, the gap between online and offline methods still exists. Okay, we made it. We finished. We read it. Here they're sampling a bunch of people, wider DeepMind research, environmental teams, intellectual infrastructure. They're doing this in JAX. That's what all the cool kids at Google don't use TensorFlow anymore. Like, nobody uses TensorFlow anymore. You got to use JAX. If you're using TensorFlow, convince your boss to switch to JAX or just switch to PyTorch and stop torturing yourself. Deadly data. I feel like chess makes sense because it's a lot of memory, right? But RTS games, I think, have a lot more possible scenarios, so harder to perfect. Yeah, chess is way more constrained versus RTS is way harder. There's so many more. To put it more formally, the state action space is way larger. What RL should we research to catch up on this? It doesn't matter. Joseph, the answer is that we've gotten to the point of humanity where you don't have to do anything anymore. This is inevitable. There's a momentum, right? Our technological progress curve has this momentum to it, and even if you were to just sit in your room for the next 10 years, you would still get AGI. There's literally no action you can take that matters as an individual human, which is terrifying, but also hopeful, I think it's great that at this point there's nothing anybody can do. The AGI is going to get here, and all we got to do is just wait. Pretty educational. I thank you for listening, Deadly Data. These papers can get a little bit intense here. Let's scroll through the here's the equation for ELO rating. That's pretty cool. What else? Behavior cloning. Here's how you do behavior cloning. Little pseudocode. This mini batch size is insane. 32,000. Like, they're definitely training this in a distributed, monstrous computer. Emphatic offline actor critic. At least they're publishing their results. This is a form of open source. It's not the code, but you could recreate the code from this. So it's a form of open sourcing. They don't tell you what the loss function is here, so I was like, are they going to open source mu0? And they're like, yep, so you just take the gradient and then use Atom Optimizer to take a step. And it's like, all right, well, what's the loss function? Well, the loss function is this. Don't worry about it. Okay, and then here you have the win rate, and you have the win rate broken down by Zerg, Terran, and Protoss. I don't know what the meta is in StarCraft, but it's actually kind of interesting how there's a huge discrepancy here. The win rate for the different races is actually, there's 77% versus 15. Zerg versus Protoss. I don't know. There's some kind of meta, right? I think one of these races is way better. Do you have any advice on how to get a certain level of knowledge where we can understand most of the paper similar to how you do? I clearly finished, but still pretty clueless. No, I still don't feel like I understand everything. You just keep doing it, and then you just understand more and more of it. But there is no secret answer. There's no secret textbook that I read that was better than any other textbook. I just have read so many papers that over time I have a little bit more knowledge than the next person. But there's still plenty of crap that I don't really understand, or I think I understand, but then I don't understand. So as long as you kind of approach anything with a kind of a novice mentality, and you're like, hey, I'm just going to read this and I'm going to understand the ones that I understand, and that's about it, and I'll be happy, and maybe I get one thing out of this paper, and then the next paper you get one thing out of that, and the next paper you get one thing out of that. And yeah, I don't know, part of these streams, it's you can tell the way that I would normally read this, I would read this in silently, right, in my head. And when I'm reading it in my head, I'm doing what I do in these streams, where I will, if I see something that I know what it is, I'll basically explicitly describe it in my head, right? So when I read this and I'm saying AlphaStar Unplugged, large scale offline, I'm like, okay, well, what is offline reinforcement learning? Okay, what is large scale offline reinforcement learning? So it's I'm creating kind of a chain of thought for every word that I know and concept that I know in my head, and that allows me to perhaps extrapolate one or two extra things that I don't know in this paper, and then over time those little extrapolations accumulate into an intuition, and so on. I don't know. Hopefully that made some sense. All right, let me take a big sip of this yerba mate, and then let's summarize this paper. All right, so today we read AlphaStar Unplugged, Large-Scale Offline Reinforcement Learning. This is a paper out of Google DeepMind, which is a AI company known for their Go and chess-playing reinforcement learning agents, also known for for their protein folding. And it's one of basically the best applied AI lab in the world. And if the hype is real, which it probably is, they're going to, they are not responsible for GPT. That's OpenAI, but it kind of came out of left field, and they're going to basically create superintelligence. So superintelligence may already be here, and it's inside a Google DeepMind training cluster, and it's basically a language model that has been put into one of these giant reinforcement learning systems, and it's called Gemini, and that's why I'm keeping tabs on these DeepMind papers, because I think they're literally a couple years away from releasing what is going to either kill us all or free us all into a utopia. Okay, so in this paper, they basically talk about how offline reinforcement learning is difficult because you basically have all this offline data, which basically means it's just a bunch of games of this game called StarCraft. So I forget the exact number of games, but StarCraft is a much more difficult game than most of the games that these reinforcement learning systems have played. because it is stochastic, so there's some randomness to it, and there's like critical hits, like there's all this kind of randomness to it. There's no such thing as a critical hit in chess. It's deterministic. There's partial observability. You don't know what the other players are doing. You can only see a limited amount of the map and so on. And there's just millions and millions of games to learn from. So it's a perfect problem to throw a bunch of compute at. So what they're trying to do is create a benchmark. They're trying to make this the new Atari, right? They want people to do reinforcement learning, but not reinforcement learning on Atari benchmarks. They want to they want people to start doing reinforcement learning that is on a more difficult benchmark, and that's kind of what they're going at. What else? Talk about the Markov decision process, which is the mathematical cornerstone for all reinforcement learning, and there's definitely flaws. And the biggest flaw is this idea of finite sets of states and actions, right? And then some transition distribution. I think that in the real world, literally this second sentence here is where it all breaks down, because finite states of sets and actions and a transition distribution and a reward function, those only exist in games. I think that we're going to eventually realize that this doesn't exist for the real world, so we're going to have to modify that. What do they got here? So here they got their reinforcement learning agent is receiving a bunch of different inputs. It's basically receiving a bunch of information about the map of the StarCraft map in the form of these feature planes, unit inputs, so the different units on the game, the vector inputs, different information about the game. They describe it in the appendices, but basically it's like this omniscient state of like everything in the game. So visibility, path, like which units are on, like how much of each mineral you have, how much the amount of health that every single unit has, and so on. So it's a little bit, it's way better. It's not playing StarCraft in the way that you're playing StarCraft, I think is the best way to describe it, where you're moving your mouse in an XY position and you're looking at a screen and you're kind of moving your eyes around the screen to look at slightly different things. That's the way that you're playing StarCraft. The way that this reinforcement learning agent is playing StarCraft, it gets like a perfect information at every single step of the game, and it can basically take perfect actions. So that's an important thing to realize. Okay, so basically the two families of techniques that they're using here is behavior cloning and then offline actor critic. So in behavior cloning, you're basically training a neural net to match what a human does. So given this current state, what action am I going to take? And the action that I'm going to take is just the action that is as close as possible to what the human did. So this is one way to do it. The other technique family of techniques here is this actor-critic technique, where you have a critic, which is trying to learn how much reward am I going to get at this particular state, right? And then you have an actor, which is trying to say, okay, well, what action should I take to maximize the reward based on what this critic is telling me? So you can think of it like a GAN, and then the behavior cloning, you could think of it like supervised training to imitate the human. So those are kind of the two families of approaches, but obviously they have their own little fancy variants of them, and they are actually combining them too. So they're like initializing one with the other, bootstrapping, and then fine-tuning. Like, it's a little bit more complicated, but those are the two kind of big buckets. This was probably the best table in the paper, where they show, was it that one? No, I think it was this one. Yeah, this one here, where they basically show you how more data wins, and you can pre-train and then fine-tune is better than pretty much everything else. And you want to include the losses. That was kind of an interesting thing there. What else? This table here showing you LSTMs are trash, transformers are better. So if you needed more examples of that, here you go. Here's another example of why you should never use LSTMs in 2023. Temperature, nice little explanation of temperature. And I don't know, that's pretty much it. That's the paper, and then they kind of go through and they benchmark a bunch of other already existing RL stuff. But so far, so good. And hopefully people start coming up with new reinforcement learning tricks, new reinforcement learning ideas that are based on this much more complicated benchmark. But you know it's going to be difficult because this is a very compute-heavy benchmark. You know, there is something to be said about benchmarks that are very cheap and simple, and I would say Go and Atari are definitely much cheaper and simpler than StarCraft 2. So, you know, it's more complicated, but it also means that you kind of got to have a huge budget to be able to actually perform experiments in it. Thanks for the session. I appreciate it, Ed. Might be a stupid question, but how long do you think until people can try to build and run AI agents and MMOs on their own labs and homes? So the first part of that question, how long do you think until people can try to build and run AI agents in MMOs? That's yesterday. Like, people have been doing that. In their own labs and homes, that's the part that it kind of falls apart. I think that the more complicated the game, the more compute that you need, the bigger your data set, the bigger your models. So you're not going to be able to train anything like this at your house. You're probably not going to be able to train anything like this at your academic cluster with 10 nodes. You're probably not going to be able to train anything like this at a startup that has a limited amount of compute. You need a huge amount of compute to be training and running these things. Maximizing PvP sides of games. Yeah, I don't think you're going to be able to win PvP with an entirely AI agent. I think you're going to have to, if you want to do that, you're better off kind of solving lower hanging fruit and then kind of becoming more of a centaur. Right? So there's this idea in chess of centaurs, which is basically a human player that has a bunch of AI agents, and together the human with those AI agents are better than a human, or better than an AI agent, even though I think at this point the AI agents are better without the humans. But we're at the centaur stage of video games, where if you had an AI agent that maybe looked at your mini-map or something, or maybe looked at your combat log and then like gave you some condensed or intelligent output from that, and then you used the output of those intermediate modular pieces, you might be able to gain an advantage from that. But to get to the point where you're training an entire AI agent that does all of it for you and plays the game in real time, I think that's not really going to be possible. We're going to have to wait for some time to do that. Okay. What are we at? 10:15. I think we're going to end it here. But thank you, Deadly Data. Thank you, Ilte. Thank you, Ed. Thank you, John. And thank you, Joseph. Thanks for the questions. Thanks for hanging out. Hope this was interesting. And see you guys next week. No stream tomorrow, but a stream on Monday. So see everybody later. Bye.